In the previous video, we looked at calculating the area between a curve and the x-axis. In this one, we're going to extend that idea to between two curves. If we wanted to calculate the area between this blue and red curve, well, if we calculated the area under the blue curve, so by integrating that blue curve, that would give us this section here, that whole section. If we then calculated the red curve, that would give us just a bit below the red bit. If we then subtracted them, we'd get the big area underneath the blue one minus the area underneath the red one, and that would leave us with the orange. And so to be able to calculate area between two curves, all you need to do is integrate the curve on top, and let's just call this A and this one B, between A and B, and subtract the integral of the curve on the bottom. Now, because when we integrate we can separate the parts, we can integrate separate parts, we can also bring it together, giving us the integral between A and B of gx minus f of x dx. So that is going to be our formula for calculating the area between curves, and the only important thing is that the gx is greater, and the only thing you need to be wary of is that the function on top must be first in the subtraction. Now it turns out that when we do the subtraction, we no longer have to worry about any areas underneath the x-axis. The act of subtracting will make anything that's meant to be negative due to the fact it's under the x-axis positive. And so when you're doing this, the only thing you need to be watch out for is what function is on top. We're going to look at three different examples. Number one, we're given the curve y equals x and the curve y equals x minus 1. Now we're not actually given any x-intercepts, and so we need to calculate that to find where this area starts. Now there are two ways to do this. The first way is that you could just use the graphing mode on your graphics calculator, plot the two graphs and find the intersection points. Now the only time that this will be a disadvantage is if the function is not just purely a polynomial, there's a chance that the intersection points will not give an exact value. If the question is asking for an exact area, you need to calculate the exact value of those intersection points. And so I would check first, but if they aren't very nice, then you can solve it by hand by just making our two equations equal to each other. So in this case, we have x equals x minus 1. We can expand the right-hand side, rearrange, and solve. That gives us x equals x squared minus x. Bring the left-hand side to the right, we get 0 equals x minus 2x. We get 0 equals x squared minus 2x. Factorize and solve. That gives us x equals 0 and x equals 2. So that means that this point is 0 and that point is 2. Now that we have our limits, we can integrate. We know that in this entire red area, the line y equals x is on top, so that will become first. So we get the integral between 0 and 2 of x minus 1, which becomes between 2 and 0 of x minus x squared minus x. I'm going to put that in brackets just so I don't make any silly mistakes with my negatives, which is finally the integral between 0 and 2 of x minus negative x is 2x minus x squared dx. Now we have our integrand. We can integrate that. We're going to get 2x goes to x squared goes to x cubed over 3 between 2 and 0, which gives us 2 squared minus 2 cubed over 3 minus 0 squared minus 0 cubed over 3. That whole right bracket is just 0. And our left bracket is 4 minus 8/3, or 4/3. And that is our final answer. Number 2. We have these two graphs, and we're told that the straight line is y equals x minus 2, and the cubic is y equals x cubed minus 2x squared. Now there are two separate areas going in here. There's the first area, which I'm going to label A1. That's where the cubic is on top and the straight line's at the bottom. And the second area, which I'm going to label A2, which is where the straight line is on top and the cubic's on the bottom. So we need to deal with these two separately because they both have a different function on the top, and then add them together at the end. Now we're also not told any x-intercepts between these two graphs, so we need to work that out, either using the graphing calculator, or you can make them equal to each other. We get x cubed minus 2x squared equals x minus 2. I can rearrange that to get x cubed minus 2x squared minus x plus 2 equals 0. Now in the integration unit we haven't been taught how to solve cubics, so you can just plug that into your polynomial solver in your calculator. Whichever method you use, you're going to get x equals -1, 1 and 2. So I'm going to draw that into my graph. That there is -1, this here is 1, and that there is 2. So in terms of areas, well, A1, that's going to equal the integral between -1 and 1 of the cubics on top, so that's x cubed minus 2x squared, and the straight line is on the bottom, x minus 2, which gives us the integral between -1 and 1 of x cubed minus 2x squared minus x plus 2. We can integrate that. We get x to the power of 4 over 4 minus 2x to the power of 3 over 3 minus x squared over 2 plus 2x between 1 and -1, which when we put in our limits we get, we should go all the way to the left hand side, 1 to the power of 4 over 4 minus 2 times 1 to the power of 3 over 3 minus 1 squared over 2 plus 2 times 1 minus -1 to the power of 4 over 4 minus 2 times -1 to the power of 3 over 3 minus -1 to the power of 2 over 2 plus 2 times -1. That gives us, simplifying, 1/4 minus 2/3 minus 1/2 plus 2 minus 1/4 plus 2/3 minus 1/2 minus 2. The quarters will cancel, the negative halves will cancel, so that gives me -2/3 minus 2/3, which is -4/3, plus 2 minus -2, so plus 4, which gives me, that's timesing by 3 to those two, -4 plus 12 is 8, -4 plus 12 is 8 over 3. That's area 1. Of course, you don't need to do that by hand, you can plug it into your calculator. Area 2, well, that's the integral between 1 and 2 of the top one, which is now the straight line, x minus 2, minus the bottom one, x cubed minus 2x squared, which is the integral between 1 and 2 of x minus 2 minus x cubed plus 2x squared, which is x squared over 2 minus 2x minus x to the power of 4 over 4 plus 2x to the power of 3 over 3 between 1 and 2. Subbing in our limits, we get 2 squared over 2 minus 2 times 2 minus 2 to the power of 4 over 4 plus 2 times 2 to the power of 3 over 3 minus, subbing in 1 squared over 2 minus 2 times 1 minus 1 to the power of 4 over 4 plus 2 times 1 cubed over 3. If you put that all into a calculator, you'll get an area of 5/12. So therefore the total area will be the 8/3 from the first one plus the 5/12 from the next one, giving an area of 37/12 units squared. Generally, if there are no units, the marking schedule will not be requiring you to write units squared, but it doesn't hurt to have it in either. Finally, calculate the area between the curves x equals 1 and the y-axis, so the shaded area. Well, we know straight away that this will be the integral between 0 and 1 of the top one, 3 sec squared x minus 2 tan squared x. Now, sec squared x is quite easy to integrate, but tan squared x doesn't have something in the table, so we need to rewrite tan squared as something else. Now, it just so happens that tan squared x plus 1 is sec squared x, which means that tan squared x is equal to sec squared x minus 1. So we can substitute that into this equation. Integral between 0 and 1 of 3 sec squared x minus 2 times sec squared x minus 1, which gives us between 0 and 1 of 3 sec squared x minus 2 sec squared x is just sec squared x plus 2. Now that as an integrand is quite easy to integrate because sec squared x goes straight to tan and 2 goes to 2x between 1 and 0. Substituting in our limits, we get tan of 1 plus 2 times 1 minus tan of 0 plus 2 times 0, which gives us a total area of 3.557 units squared to 4 significant figures. Generally speaking, these questions aren't going to be any more difficult than the area under the curve. The thing that will trouble you is either finding the intersections, accurately mapping the different areas if there are separate areas, or just the integration. So if you're comfortable with your integration skills, these questions shouldn't provide any extra challenge.